In this lab, I will demonstrate the implementation of different chunking strategies and how they contrast in terms of retrieval quality, precision, and context preservation. I will use Amazon Bedrock for generating embeddings and OpenSearch for storing and indexing vectors for retrieval. In preparation of this lab, I have created an OpenSearch domain using OpenSearch service in AWS. In the domain settings, there is the domain endpoint that we will use when connecting with OpenSearch. I have used AWS Secrets Manager for safely storing OpenSearch credentials in a secret that I will access from my code. And I have provided execution role of my notebook, permissions to invoke Bedrock and Secrets Manager APIs. As a first step, we will set up the environment by installing libraries such as Boto3, which will help us interact with AWS services, and OpenSearch Python libraries for vector indexing and retrieval. TQDM will help us see progress bar at the time of chunk indexing. Let us import the classes that we need. In this cell, I have defined two functions for interacting with AWS Secrets Manager. In first method, we are creating a client using Boto3 for AWS Secrets Manager, and then we are using this client to get secret value using the secret ID. Depending upon whether the secret is of type string or base 64, we are retrieving it from the response and returning it in a JSON object. A secret is basically a dictionary of key value pairs, and in the second method, we are extracting the value for the key password. In this cell, we are configuring the parameters for creating a connection with OpenSearch service. We have set up the OpenSearch host, the username, and the password that we are extracting from AWS Secrets Manager. In this cell, we are creating a Bedrock runtime client using Boto3. We will use this client for invoking the embedding model to generate the embeddings for the texts that we will index in the vector store. And then we are choosing the embedding model for generating the embeddings, which is Titan embedding model. It generates embeddings of 1536 dimensions. In this cell, we are setting up an OpenSearch connection by passing in the host name, the credentials, and values for security parameters. We're storing this connection in the client named client that we will use throughout this lab. In this cell, we have defined a helper function for creating the vector embedding for the input text. We are invoking the embedding model using Bedrock, and we are passing in the text. And in the response, we are getting the embedding that we are returning. Next, we have defined a sample document for chunking, indexing, and retrieval. This will help us contrast different chunking strategies. The text is part of a hotel operations guide. Notice that there is a document ID and a title with this document. Let us read the text to get familiar with our search space. Housekeeping teams should inspect bathrooms, replace used towels, and vacuum carpets during each room turnover. When guests report a dirty room, the front desk should log the complaint, alert housekeeping, and offer room re-clean or reassignment. Managers should track repeat complaints by floor to identify staffing gaps. Preventive maintenance includes checking air conditioning filters, plumbing fixtures, and lighting during weekly inspections. The first chunking strategy that we will explore is fixed size chunking. In this approach, document is divided into chunks of predefined fixed size with an overlap between the chunks. Fixed chunking is simple, scalable, and very widely used, but it has a drawback. It can split the sentences and concepts in the middle. Let us look at the implementation. Here in this function, we are passing in the text, the chunk size, which is 100 characters, and overlap, which is 20 characters. We start at the beginning of the text and extract the chunk size and then create the sliding window, which is chunk size minus overlap, to extract the next chunk. We keep doing this till we reach the end of the text. So it's a very simple implementation. Let's chunk our document using fixed size chunking. Each line is one chunk here, and as you can see, the chunks are split mid-sentences and even mid-words because we are using character level chunks. You can split by words, but even then, sentences will be split midway. Next chunking strategy that we will explore is recursive chunking. In this technique, we create chunks of a maximum size without breaking sentences or ideas midway. So let us see how it is implemented. Here we have a function recursive underscore chunk that takes in text that we have to create chunks for. Maximum size of the chunk is 120 characters. Next, we have a list of separators which defines the boundary of the hierarchical structure of the document, such as sections, paragraphs, sentences, etc. For example, sections could be divided using 2 lines, paragraphs using 1 line, sentences using a full stop, and words using a space. Our code will first begin by separating the document or text using the first separator, which is 2 new lines. If the resulting chunks are small enough to fit into 120 characters, we will stop there. If any chunk is larger than 120 characters, we will use the next separator, and so on. So this is what we are doing in this method called split text. We are basically starting from the first separator and we keep going to the next separator till we reach a chunk size which can fit into 120 character. But if you notice in any of this, we are not splitting the sentence or paragraph midway. We are trying to contain either the paragraph or the sentence within 120 characters here. Let us chunk our document, and here we are replacing some of the white space and new lines. And as you can see, in this case, our chunks contain intact sentences for most part, except for here and here, but that is because this sentence is more than 120 words and we had to split it by a space which split the sentence into 2. Maybe what we can do is we can increase this size. What if we do it 150? Let's rechunk it. And if you see, in this case, we have 4 chunks and each chunk has the full sentence because each of these sentences could fit into 150 characters. The next chunking strategy that we will explore is semantic chunking, which, as the name suggests, tries to group sentences together based on conceptual similarity, rather than purely on size or formatting rules as with the previous 2 techniques. This often produces more meaningful chunks because related ideas remain together inside the same embedding. However, it is computationally more expensive because we need to generate embeddings to compare topic similarity between subsequent sentences. Let us look at the code to understand how this is implemented. First, we are defining a method to compute cosine similarity between two embeddings using NumPy library. Cosine similarity measures vector similarity by measuring angles in the directions of the vectors. If the angle is 0 or small, then vectors point in the same or similar direction and are closely related. And if the angle is large, then they are unrelated. In this function, we return 1 for most related. And then we have this another function called semantic chunk, which basically creates these semantic chunks. It takes in the parameter text, which is the text that has to be chunked, and a threshold, which is the threshold of cosine similarity, above which sentences are considered similar. Inside the method, we are first splitting the text into sentences by splitting it by the full stop. We are storing these sentences in this list, and then we are going over this list, creating an embedding of the current sentence, comparing it with the previous sentence's embedding, and if they are similar, we combine them in the current chunk, and if their similarity is less than the threshold, then we create a new chunk with the new sentence and we close the previous chunk. So this way we observe topic changes between subsequent sentences and we split our chunks according to that. As you can see, this chunking strategy requires generating embeddings for sentences using the method that we had created above. Let's chunk our document. And as you can see, this is even better than recursive chunking, which had split this idea into two sentences. In this case, we have combined the idea together in one chunk, even if it's two sentences. And here we have two other chunks. Next, we will review hierarchical chunking, which is commonly used in advanced systems when we are dealing with structured documents. Hierarchical chunking is useful if the use case requires that we pass the parent sections with retrieved chunks. For example, if related information is organized under sections, then when a paragraph matches the query, the whole section can be returned to the end user as it can be beneficial. The way this is implemented is that we take the larger sections of the text from document and treat them as parent node. We split the parent node into smaller child nodes that we embed and index in the vector store. We maintain parent text and the mapping with its child nodes outside of vector database in metadata. And at the time of retrieval, we add the parent text to the retrieved child chunks by looking up the metadata. Let us look at the code. For simplicity, I have used list to hold the parent nodes. You can have a tree-like structure. We have two methods, tokenize and detokenize. These methods use regular expressions to split the sentence into words in tokenize and to put together a sentence by combining the tokens in detokenize. So basically this one splits the sentence into words and this one creates a sentence from the words. Inside the hierarchical chunk method, we take in the document with attributes such as ID, title, because this is a dictionary. So we take all these attributes and then we specify the parent size, which in this case is by tokens or words, not characters. So this is 80 words and child size is 30 words and overlap in this implementation is 8 words. The first step is to define the sliding windows, which is parent size minus overlap and child size minus overlap. We need to keep moving this much after we extract a chunk, then we move this many steps to the next chunk. As a first step, we are extracting a parent section from the text based on the size that we have specified here. We are saving this parent section in this hierarchical parent rows list that we had created. This is the metadata list that we have created. And we are assigning every parent a unique ID called a parent ID. We're also saving the chunk as plain text and document ID and title for maintaining the metadata of the document. And in the next step, we are splitting the parent text into child chunks depending upon the child size. So these child nodes are added to another list called rows. This rows is what is going to be returned, and this is what will be indexed in the vector database. The other list, which is hierarchical parent rows, is just a metadata that we will maintain, and we will use it to combine parent text to the retrieved child chunks at the time of retrieval. So that's the implementation. Let's run it. And here you can see we have different child nodes. Each of them has 30 characters with an overlap of 8. And each of them has a unique ID and a parent ID. So this is the child ID and this is the parent ID. And this is what we saved in our list of metadata. This will help us look up the parent node. Now, before we can index our chunks, we need to create the index. So in this cell, we are creating the vector index. First, we are defining the index. KNN equal to true means that the index supports nearest neighbor similarity search of embeddings. We are defining the vector similarity search by setting KNN to true. And then we are specifying that each indexed record contains the chunk text, the embedding for the text, which has dimension of 1536, and a metadata called chunk type. This will help us compare different chunks from different chunking strategies. And then we are deleting the index if it exists and then creating it. In this cell, we are indexing the chunks that we have created using different chunking strategies. We have created this method called index_chunks that goes over this list, and for each chunk in that list, it first embeds it and then creates a document structure by adding the plain text chunk, the embedding for that chunk, and the type of the chunk, which is the metadata. And then it indexes it in our index. So we have indexed chunks from all chunking strategies now. In this next cell, we are defining a method for performing vector similarity search using a query against our index. We take in the query text, and the first step is to embed it using the same embedding model that we used to embed the vectors for indexing them in the vector store. It is important for accurate retrieval to use the same embedding model. We then specify the type of the search, which is KNN, and we pass the query vector, and we also pass K, which is the number of closest vectors that the search has to return. If you remember, the hierarchical chunking requires retrieving the parent text and adding it to the chunk. This is what this method is doing. It is finding the parent for the retrieved chunk using the metadata list that we had created. And here we are calling the vector search and printing the results in this method. Now let's search when our toggles changed. That's our query string. So let's see what we get. So the first chunk is from the semantic chunking technique, and it is providing us information about when toggles are replaced, and it is also giving us additional information about room reclean or reassignment, which is semantically similar to replacing the towels because you change the towels at room reclean or reassignment. In recursive chunking, we get the sentence that talks about replacing used towels. It's a full sentence, so this is pretty good as well. This is another one we got from Recursive, and this actually returns the second sentence because semantically it matches the query text even though there is no word towel here, but when you reclean, you replace the towels. Then we have the hierarchical chunk with the same sentence and its parent node to give us the full context of when and how the replacement happens. So this is really good if you want the full context. And in the fixed one, we have housekeeping teams should inspect bathrooms, replace used towels and vacuum carpets during, and it's cut off in between. So as you can see, depending upon your use case and the amount of accuracy you are looking at, you should pick the right chunking strategy. Typically, Recursive is easy to implement, is scalable, and does not have the overhead as hierarchical or semantic have in terms of using an embedding model or maintaining a metadata. Let us run a few more queries. How should cleanliness complaints be handled? And then we have the right response from Recursive. It clearly talks about when guests report dirty rooms, then this has to be done, full sentence. Semantic also talks about the same thing. It has a little more context though. And in fixed, we have a half sentence again, but that's because our fixed chunk size is small. If we increase it, maybe we'll get better answers. I hope this lab provided you with good intuition into different chunking strategies and their benefits and drawbacks. Many vector stores provide inbuilt functions for different chunking techniques, but if your workload is complex and you need more control to build for portability, then implementing your own chunking methods can be beneficial. Chunking is a foundational design decision that strongly affects the retrieval quality, context preservation, latency, scalability, and overall effectiveness of your RAG system. So you should spend some time to evaluate the right chunking strategy when designing your system.